So how to find the line, how to find the orientation of the line that fits your points best, and what is actually best fit. So the method we are going to learn is called least squares methods, meaning you minimize squares, you minimize some squares. So least means the smallest possible, right? So let's talk about this. Well, first of all, let's start with intuition. You can see a data set where I have both x and y. You can see the data points on the screen. And then our goal is to find which line fits these points best. For example, if I make this line, does it fit point well? Well, from my point of view, yes. Of course, you can see that this point varies a little bit far away from this line, so this error will be large. But for the other points, the error is relatively small. So to me, it looks good. But now I have a new line position. And you can see that, for example, this error will be definitely small. Some errors will be larger. Some errors will be almost zero, like this one, right? Maybe this line fits the points better. Or maybe this line. You can see that in this case, you have 3 points with almost zero error of prediction, right? Or maybe this line. So how to find which of these lines are best? Let me show you all these lines together here, right? So how to find the best fit and how to define the best fit? Well, apparently the idea of the best fit, it means that it should serve all points equally well. So we need to find something that makes the best fit for all the points. Of course, some points will be fitted better than the others, but we need to find kind of an overall solution, right? The compromise. And this is how to do it. Well, you remember what is error of prediction. It's a difference between the real y value and the predicted y value, right? So if we define the error of prediction for every point in this data, so we have first point, second point, third point, and so on and so forth. So we have n points. We have n error of predictions, how far every point, predicted value for every point, is from the real y value, right? Now, the idea, we need to summarize it. We need to calculate statistics of all these errors and try to make it as small as possible. Well, in general, of course, we can take an average error. But we know that average error will be zero because some of the errors are negative, some of the errors are positive, so the average error is always zero. Like you remember in variance, when we compute distance from x to m, from the values to the average distance also zero. But we can use the same trick as we did in variance. If we square the errors? So if we square the errors, so we square these distances, in this case the distances will be positive. We don't care if it's negative and positive. We would like to minimize the distance itself, right? And then we can compute the average squared distance. But in this case, actually, we don't need even to compute average, because what you need to do is to compute a sum of squared distance without dividing them to n. Because if you minimize the sum of squared errors, it will be automatically the smallest average possible, right? Because you simply compute average squared distance by dividing to the number of points. So that's the overall idea. We need to compute a sum of squared errors by squaring these distances and taking a sum of them. And then that's just another notation for this, a short one. And then the idea is that the baseline should minimize SSE, so it should make the sum of squared errors as small as possible. But do we have one single position of the line that indeed minimizes this point? So let's investigate how sum of squared errors depends on the parameters of your line. Well, first of all, let me show you the same examples that I showed before, but now I also show the sum of squared errors. For example, in this case, it's the first phase. The sum of squared errors is 47.5. The second case, it's 47.94. So from that point of view, you can see that they're almost the same, but this one is a little bit better, right? This is apparently the worst of these three. It's 56.44, and the last was actually the best one. It's difficult to see it visually, but if you compute the statistics, you can clearly see that this is the winner in this case, right? Now we need to find out how to find this winner automatically. Well, look at this plot. You have x, you have y, right? And the blue are data points, and they follow these. So this is the theoretical model, and I have no noise here, so this is a perfect case. The gray lines are different models. You can see that I try to fit points with this line, with this line, with this line, with this line. You can see slope of these lines is the same. They vary only by the intercept, right? Also these lines, slope is the same. Slope is 0, by the way, in this case, right? And I vary intercept. Then I have these lines, the same slope and different intercept. Then I have these lines and these lines. So I have different slopes and different intercepts. I have different combinations of B0 and B1. These are the combinations. You can see that, for example, here, B0 is 0, then it's 2, 4, 6, 8, minus 2, minus 4, minus 6, and minus 8. So this is B0. This is the when you see the parallel lines, so every parallel line, it's different because you have different B0, the intercept. Now you see B1, right? So it says minus 1, it's this one, minus 1, right? Then you have 0, it's these lines. Then you have 1, it's these lines. Then you have 2, it's these lines. And then you have 3 and 4, then it's barely visible here, right? So and then I have different combinations. For example, this model is y equal to minus 8 minus x, minus 1x, right? So this is B1, this is B0. And then you can see that, well, the sum of squared errors is 5,841. So it's one of the largest. Actually, it's the largest sum of squared error. You can see I use gradient from yellow to blue. The yellow, it's the largest sum of squared errors, and the blue is the smallest one. And then you can see that actually I have one single point, it's this one, where the error is 0. And that's exactly the black line here, right? So you can see despite all these combinations, I have one single minimum, one global minimum that finds the best line fit. Okay. Now, if I repeat this again, but now you can see that, for example, using these lines is crazy. I mean, definitely we don't have a good fit by this line, right? So let me minimize, let me make a smaller number of lines, and these lines will be closer to the theoretical line, right? So this is the case. So you can see I use 1, 2, 3, 4, 5 different slopes. And then I use 1, 2, 3, 4, 5 different intercepts. So I have 25 lines, 25 gray lines that you see on the plot. But again, you can see, for example, if you take this one, what is this? It's B0 equal to minus 2 and B1 equal to 1, right? So the model is y equal to minus 2 plus x. And this is, you can see that now my intercept is 0. I changed the points for the sake of clarity. And this is the real model, right? So you can see the real model is different by a factor of 2 for the intercept, right? And that's why the sum of squared errors is quite large. But again, you can see that this is a bit smaller, a bit smaller, a bit smaller, large again. You can see that the more far you go from the real B0, the larger error becomes, right? Also, the more far you go from the real B1, you remember B1 is 2, right? So the error gets larger. But if you have the correct B0 and correct B1, you get the smallest error. In this case, it's 0 because I don't have any noise in this case, right? Now let me add some noise. So in this case, I have noise. You can see the blue points, they are a little bit scattered around line, but the equation of line is still the same. Look, now the situation is different. We first of all don't have the 0 error, but still, if you find the smallest error possible, this is the smallest error in this case, and you can see that indeed you have B0 equal to 0 and B1 equal to 2. So far, we found out that we always have one global minimum. We always have one single solution that gives you the smallest error. What instead of this 1, 2, 3, 4, 5, and so on discrete number, I get more. For example, I have like thousands of different B0s and thousands of different B1s. In this case, you will have, it's not thousands, of course, but still pretty big number. You will have a solution like this, so you cannot distinguish lines anymore because they are very close to each other. But look at this pattern. Can you see that indeed you have one single minimum again? And what this pattern is? Actually, it's a parabola. It's a paraboloid, so to speak. So this is the convex surface like this. It looks like this. So this is the error. So this is the error. So this is B1 and this is B0. And you can see for different B1 and B0, you have different errors, but you always have this point which has the smallest error possible. So that's what we call a convex function. So it means that error of linear, sum of squared errors of any linear regression model is a convex function. So it means that it always has one single minimum. And that's what makes us safe in this case. So it means that there is always one single solution. There is always B0 and B1 that gives you the smallest error. Okay. How to find them? Well, strictly speaking, what you can do, you can find derivatives of this function. So you can take a derivative of this function. So you can take, for example, you remember what is error. Error is y minus b0 minus b1x, right? Because this is exactly what yp is, right? Then the squared error will be a square of this. And then you take a sum and take a sum. And then you simply take a derivative of this sum. You just simplify this expression, take a derivative, and so on. I'm not going to bother you with these derivatives. You can try to solve it if you still remember the calculus. But my point is that there is a single solution, and the solution looks like this. So the solution, the best line fit, is when b1 is a covariance between x and y divided to the variance of x. Once again, it can be mathematically proven. You can try to do it yourself. And b0 is when you take average of y and subtract b1 times average of x. These two expressions give you always the coefficient that makes the error smallest possible. Okay. We can actually simplify it. If you remember from the previous case, we have the sum of squares, right? So you can see that this is the variance. It's a sum of square distances from x and m divided to degrees of freedom. And then covariance is a sum of distances between x and m divided to n minus 1, right? And then you can see that this part is this, and this part is this. And since both have 1 divided to n minus 1, if you take covariance and divide to variance, this n minus 1 will cancel out. So therefore you can simplify this expression by just using the sum of squared values. This is just a reminder from the previous learning sequence. You remember this is what SSXX is, sum of squared distances. Here it's also sum of distances, product of two distances, right? So this is the simplification. So you simply take sum of squared distances between x and average and y and average, and divide to sum of squared distances between x and average. Okay. So that's it. Now you know how to find the line that fits your point best, meaning minimizes sum of squared errors, and this is exactly what least squares algorithm or least squares method is. Let me show you a simple example. So in this case, you can see that I have a sample of size 5, and it's simply 5 persons with different height and weight values. So let's make a fit. Let's do it manually. Well, first of all, I take a sum of this value. So this is a sum of x and sum of y. And I can use this sum to calculate average values. I simply take 850, divide to 5, and I got 170. 350, divide to 5, and this is 70. So this is average height and average weight of my sample. Now I compute distances, right? So distances between x and m and distances between y and m. So it's simply, for example, 150 minus 170 will be minus 20. 160 minus 170 will be minus 10, and so on and so forth. So these are just the distances. Then I compute the squared distances for x and product of these two distances in order to get the covariance, right? So this is the sum of squared. So this is the squared distances. So minus 20 squared is 400, minus 10 squared is 100, and so on. And then minus 25 times minus 20, you remember this is the product of distances, will be 500. Minus 10 times minus 15 will be 150, and so on, right? So here you have just a mirrored. Now I compute sum of squared distances. So this is the sum of squared x distances, and this is a sum of products of x minus m and y minus m, right? So this is the sum of products of these two distances. And now I can compute slope, because slope is simply a ratio of these two sum of squares. So the slope will be this one divided to this one, and that's the slope, 1.3. So it means that every time I have a person who is 1 centimeter taller, I expect this person to be 1.3 kilograms heavier. So that's based on my sample. This is the estimation of the effect of height on weight. Now I can also compute the intercept. In this case, intercept has no physical meaning, but I have to do it. Otherwise, I cannot use this model mathematically. So intercept in this case is minus 151. It's a weight of person who has height equal to 0. So once again, it has no meaning, but mathematically it must be computed. So that gives me my model, which is simply y equal to 1.3x minus 151. So this is the model. This is how weight can be computed based on height. Now let's check that our computations are correct. I will simply go to R and enters this data. So this is how to do it. So I enter x values, I enter y values, and then you remember we already used this function in the previous learning sequence. That's what makes a linear model. LM, linear model, y depends on x. And these are the regression coefficients. Look, so this is the intercept, minus 151, exactly what we got, and the slope 1.3, exactly that we got. So all our calculations were correct. At least they are in agreement with what we get in R. Okay. Now we can also compute the predictions, right? So how we compute predictions? We get one particular x value, for example, 150, right? So x equal to 150. Then we have y equal to 150 times 1.3 minus 151, right? If you take 150 times 1.3, you will get 200, right? Oh, sorry, it's not 200, it's 195, right? Minus 151. Let me just remove it. It gives you exactly 44, and that's exactly what you have here. So this is the predicted y value. And then you can just repeat it for other x values to get these predicted values. And then you can see that the predicted values do not match the y values. It's only in this case you have a good match, but then you have some errors as well. Okay. So we have all together. So we have the x value, we have y, we have yp, you have regression coefficients and all the statistics. Now look, this is how the model looks like, right? So the blue points are the original data values. The red line is the line that we just made with this slope and with this as intercept. And the red points, you can see the small red points, are the predicted values. So the predicted values always lie on the model, right? So for example, if you take this one, you can see this is 85 because it's exactly y equal to 85. And this is 83 because yp equal to 83. And then you can see that it corresponds to x equal to 180. So this is the case. This is the case. Okay. Now, if I change the scale of this Cartesian system, so you can see here we have 0, here we have 200, minus 150 and 100. Now you also can see the meaning of the coefficients, right? So you can see when x is equal to 0, this point where you cross the y-axis will be exactly minus 151. And then if you take this and these two sides, right? So it's just a rectangular triangle. You can see this is 130, this is 100. Because you remember why this is 130. You remember this is minus 151, right? And what is this? This is what you have y equal to if x equal to 100. If x equal to 100, then it will be 130 minus 151. It's equal to minus 21. So this y is minus 21. So the difference between minus 151 minus 21, it's exactly 130. So in this case, I have negative because I swapped the points, right? And this is 100, and then you can see if you take a ratio of 130 and 100, the slope of this angle will be exactly 1.3. So indeed, the model looks like we expected to see, right? Good. Now we need to find out how to define the quality of this model, how well it fits the points, how much of y we can explain by knowing x, how much y depends on x. So all the things will be discussed in the next video.